Welcome to Computer Vision, where we explore how machines learn to see the world through powerful algorithms. We'll journey from raw pixels to complex perception, understanding how machines interpret and make sense of images. Now, let's dive into the core mathematical formulae that underpin various image processing techniques. These are the fundamental mathematical tools that allow us to manipulate and enhance digital images effectively. First up, we have the contrast adjustment formula, which helps us modify the visual impact of an image. The adjusted pixel I prime of x, y equals alpha times the original pixel I of x, y plus beta. Here, I of x, y represents the original pixel's intensity at a specific coordinate x, y, and I prime of x, y is the new, adjusted pixel value after applying our formula. Alpha, written as the Greek letter alpha, is our contrast factor, controlling the image's overall contrast. Beta, represented by the Greek letter beta, serves as the brightness offset, adjusting the image's luminosity. In essence, this formula allows us to finely tune both the brightness and the contrast of an image. If alpha is greater than 1, contrast increases. If alpha is less than 1, it effectively decreases. Meanwhile, beta directly controls the overall brightness, shifting the entire image's luminosity. Next, we have histogram equalization, a powerful technique to improve image contrast automatically. The equalized pixel I prime of x, y equals the cumulative distribution function of original pixel I of x, y. Again, I of x, y refers to the original pixel's intensity value in the image, and I prime of x, y represents the new, equalized pixel value after processing. CDF stands for cumulative distribution function, which maps pixel values based on their frequency. This method enhances contrast by thoughtfully redistributing the pixel intensities across the image's dynamic range. It maps each pixel value to a new range, determined by its cumulative frequency within the image. Moving on, the convolution operation is a cornerstone for many image filtering tasks. The new pixel I prime of x, y is the sum of original pixel I at x plus I, y plus j, multiplied by the kernel k at I, j. Here, I of x, y again represents the original pixel value at its image coordinates, and I prime of x, y is the new pixel value resulting from the convolution operation. K of I, j refers to the coefficient of the kernel, or filter, applied to the image. Essentially, convolution applies a small filter, known as a kernel, across the entire image. This operation is crucial for tasks like blurring, sharpening, or detecting edges within an image. Finally, let's look at edge strength, a metric to quantify the presence of edges. The edge strength E of x, y is the square root of g sub x squared plus g sub y squared. E of x, y denotes the calculated edge strength at a particular pixel location x, y. G sub x represents the image gradient, indicating intensity changes along the x direction. Similarly, g sub y represents the gradient in the y direction, showing changes vertically. This formula measures the overall magnitude of intensity change present at a specific pixel. Higher values for E of x, y signify stronger, more prominent edges in the image. Now, let's explore the key performance metrics used to evaluate computer vision systems. These metrics help us quantify how effective our detection and segmentation systems truly are. First, we have precision, a crucial metric for understanding the accuracy of positive predictions. Precision is calculated as true positives divided by the sum of true positives and false positives. True positives, or TP, are instances that were correctly identified by our system. False positives, or FP, are instances that were incorrectly identified as positive. Precision measures the proportion of correctly identified positive results among all positive predictions. A high precision value means our system generates fewer false alarms, making it more reliable. Next, let's discuss recall, which measures our system's ability to find all relevant instances. Recall is true positives divided by the sum of true positives and false negatives. Again, TP stands for true positives, the objects correctly identified by the system. False negatives, or FN, are the objects that the system failed to detect or missed. Recall assesses how well our system can identify all actual positive cases, minimizing misses. A high recall score means our system is very good at finding most of the relevant objects. The F1 score provides a single, balanced metric by combining both precision and recall. F1 score is 2 times precision multiplied by recall, divided by precision plus recall. Here, precision refers to the value we calculated using our first formula, and recall is the value derived from our second formula, as we just discussed. The F1 score is the harmonic mean, offering a balanced view of both metrics. It gives us a single value that effectively balances both the precision and recall performance. Finally, we have intersection over union, or EOU, a common metric for object localization. EOU is calculated as the area of overlap divided by the total area of union. The area of overlap is the common area shared between the predicted and actual bounding boxes or segments. The area of union is the total area encompassed by both the predicted and actual regions. EOU measures how accurately the predicted bounding box or segment overlaps with the ground truth. It's widely used to evaluate the accuracy of object localization and segmentation tasks. Let's now explore the core concepts behind object detection, a vital area in computer vision. Object detection focuses on both identifying and precisely localizing objects within visual data. Its definition involves identifying different objects and pinpointing their exact locations in an image or video. This means not just knowing an object is there, but also exactly where it is within the visual frame. A key concept is bounding boxes, which are rectangular frames around detected objects. These are simply rectangular boxes drawn around each identified object to show its location. We also use class labels, which are names assigned to each detected object. These labels act as identifiers, telling us exactly what kind of object is inside each bounding box. Object detection has numerous practical applications across various industries and daily life. From traffic surveillance and autonomous driving to medical imaging, its uses are widespread and impactful. Let's explore the fascinating world of object detection techniques, a core task in computer vision. We'll trace its evolution from traditional feature engineering methods all the way to modern deep learning. First, let's look at some of the foundational traditional methods used for object detection. HAR cascades are a machine learning method, utilizing cascade classifiers and specific HAR features for detection. HOG plus SVM combines histogram of oriented gradients features with support vector machines for robust object recognition. Now, let's shift our focus to the powerful deep learning methods that have revolutionized object detection. YOLO, or You Only Look Once, is a real-time system that predicts bounding boxes and class probabilities directly from full images. Faster RCNN is an advanced extension of RCNN, employing region proposal networks for achieving very high detection accuracy. Now, let's delve into the various approaches used for face recognition, a crucial biometric technology. This involves identifying individuals by analyzing and comparing their unique and distinctive facial features. The first step in face recognition is always face detection, which locates faces within an image. Face detection specifically means accurately finding and localizing human faces within an image or a video frame. Next, we have feature-based methods, which rely on extracting specific characteristics from faces. These include eigenfaces, using PCA, and Fisher faces, using LDA, both for effective dimensionality reduction. Deep learning methods have significantly advanced face recognition, offering superior performance and robustness. These methods often utilize convolutional neural networks, or CNN, and models like FaceNet for high-accuracy recognition. Evaluating the performance of face recognition systems is critical to understanding their effectiveness. Performance is typically assessed using metrics like accuracy, false acceptance rate, and false rejection rate. Let's explore image segmentation, a fundamental computer vision task that partitions images. This process involves dividing an image into meaningful regions or distinct segments for further analysis. Thresholding is a simple method that segments images by applying specific intensity thresholds to pixel values. Region-based methods work by growing or splitting image regions based on the similarity of their pixels. Edge-based segmentation focuses on detecting sharp boundaries and discontinuities to define distinct segments. Clustering-based methods, like k-means, partition images into groups or clusters based on pixel properties. Deep learning-based approaches utilize convolutional neural networks for pixel-wise classification, such as with FCNs. Now, let's dive into the canny edge detection process, a widely used and robust algorithm. It's a multi-stage algorithm specifically designed for highly robust and accurate edge identification in images. All right, let's wrap up our discussion with a quick summary of everything we've covered today in computer vision. Here are the key takeaways, the most important points you should definitely remember from our session. First, image processing manipulates visual data to extract meaningful information, which is its core purpose. Object detection identifies and localizes objects within an image, utilizing diverse and powerful techniques. Face recognition is a specialized area, focusing on identifying individuals based purely on their unique facial features. Image segmentation is crucial for dividing images into distinct, meaningful regions, enabling detailed analysis. Lastly, performance metrics like precision, recall, F1 score, and EOU are vital for evaluating model effectiveness.